Hello YouTube. If you're new to this series, there's links in the description and up there that you can click on to watch a playlist or to view the playlist for this series. Also, this is a second hydro system that I've built. If you want to see the first one, which was a water wheel at my old house, again, links down in the description and up in the corner. So what is a penstock? Well, it's just a method of conveying water from its source down to a turbine. For the rest of this video, anytime I say penstock, I mean pipe. Or pipe and penstock are, in this case, interchangeable. So first we have to decide which materials we're going to use. The first one that some of you might think, well, actually maybe not most of you, but as an option, at least in large commercial settings, is steel. Now steel is expensive, which is the main reason that I'm not using steel, but also it's hard to work with, it's rigid and heavy. I have a pretty steep hill that I have to carry everything up, so that's not going to work. Also, the hill's not flat, and any pipe that I use is going to be resting on the surface, so it would have to conform to the undulations. Steel's not good for that. The next option, commonly you'd see this in the house, is PVC. Well, actually a house would use like CPVC and drain is PVC, but whatever. But you can get pressure rated PVC. As opposed to steel, it's a lot lighter. It's a little bit more flexible. It's a lot cheaper. A big downfall to it is it's brittle, especially when it's cold or exposed to sunlight. Again, in my case, I'm not going to be burying my pipe, so exposure to sunlight basically kills PVC as an option. Unless I went with ABS, but again, it has the other drawbacks, and it's a little bit more expensive than my final option, polyethylene pipe. Polyethylene pipe is a type of plastic pipe, comes in a black coil. You commonly see them around hardware stores. It's lightweight. It's flexible, it's easy to work with, it's cheap, all of the fittings that go with it are also cheap, and it's pretty durable. Also, exposure to cold and sunlight is basically not an issue with it. The only potential issue with polyethylene is because it comes in a big coil, is getting that big coil up the hill. So we're going to have to deal with that. I have some ideas, we'll see. And here's the pipe that I went with. Just kidding. Not this stuff. This is stuff I use to run water for the house. It's only 3/4. 3/4's not big enough. We're trying to flow 15 to 30 gallons per minute. This isn't going to do it. Give me your wallet. That's not a knife. This is a knife. Had a little fun there. Been thinking about that for a few months, actually. So this is the pipe I went with. And actually, one moment. That's it. This is 800 feet of 1.5-inch polyethylene pipe. I got it in 2 separate rolls. One roll is 500 feet, rated for 100 psi, and that'll be the uppermost section. And then another 300-foot roll, rated at 125 psi, and that'll be for the lower portion. So each one of these rolls is around 100 pounds. One of them is, I think, 90 pounds. The other one is 110 pounds, and they're 5 foot in diameter. Now, you can expect a big fight trying to get this unrolled and up the hill, and I kind of am. The way I think I'm going to do it is I'm going to build some sort of spool for the inside, 2x4s in a cross pattern with a hole drill in the middle, and so I'll have like an axle there, and that'll allow this to unspool as I winch it up the hill. Now, I'll probably be able to drag a large portion of this up the hill, but I imagine once I get about maybe a third or a half of the way up the hill, it's going to be too hard for me to pull, in which case I'm going to have to be doing this with some sort of ratchet winch or a drill winch, which I still haven't sourced yet, so that'll be a purchase that I'll have to make soon. So this is 1.5 inches. Obviously it comes in many different sizes. You saw the 3/4-inch pipe. 1/2-inch pipe is common. You can also get this in much larger sizes, like 8-inch, 10-inch, 12-inch. Those don't come in a spool though. Those come as straight lengths, and they have to be welded together with a special machine. So obviously, because I'm doing a smaller size pipe comes in a spool, I don't need the welder, which is nice. There's at least 2 cases of people working with pipe larger than this that I've seen on YouTube, and each time they had a bit of a trouble dealing with it. The first one would be Chris Harbor, and he got some pipe, I think it was like 3 or 4-inch, and it came in a spool, and he had to use his excavator and a tractor to unwind it. I'm not doing that. And again, I'll have links to these, you know, maybe over there or in the description. The other case I've seen for pipe like this being laid is 2-inch pipe, and that's Pure Living for Life out in Idaho somewhere, and they had a heck of a time trying to unspool their 2-inch pipe.
All right, she's wild and free. Based on that 3/4, I don't have high hopes for this stuff. Oh yeah, she's heavy too. I almost feel like you should probably, I think somebody even told me this, just straighten this out and let it stay straight for a whole day. Let the kinks come out of it. Oh, wow. I'm not really a small guy, but wow, this stuff does not take instructions well.
Wow, this looks fun. What's the fun factor on this hose? Was it the inch wasn't this bad, right?
No. And it's 3/4.
Oh. Do we have inch?
No.
Oh.
So I'm going to try to not do what they did. Again, links, you know. So why 1.5 inches? Well, I'm going to show you calculations in a little bit, but it essentially comes down to 1.5 inches is sufficient for 95% of the time, or at least I assume that's what it would be. Sorry, if you see snow looking stuff, it's actually like from trees. It's not snowing. So only once after a large portion of rain, a very wet season, like all of fall, I think it was one of the earlier videos in this series, I saw up to 30 gallons per minute. This would still flow 30 gallons per minute. The problem is when you start flowing such large amounts of water, or gallons of water, it's traveling faster through the pipe. And as water flows through a pipe, there's friction. And if you have too much speed, the friction increases significantly. We'll see later, I'll show you the numbers. Even going 1.5 inches at the peak flow I've ever seen, I'm not losing that much potential power by going with a smaller size. So I know in one of my previous videos I had said it would be like $800 in pipe, but I went with this for a few other reasons too besides the price, and this was cheaper. That $800 was going to be for 2-inch pipe that I thought I would need, but it turns out like I visited during the middle of winter and it's not flowing 30 gallons per minute, it's flowing 15 or 20 gallons per minute, so I don't need 2-inch. I thought maybe in the winter it'd be flowing 30 gallons or more all winter, but no, it's not. So I don't need to worry about going with a bigger pipe. 1.5 inches is sufficient. And for that reason, I didn't spend $800. Actually, 2-inch pipe would have been $812, and I would have had to go pick it up myself. Actually, still had to pick this up. And this was $486. Now, every place around here, which is kind of stupid because I live in a place near 2 factories that make this pipe, I couldn't find it cheaper. The factories don't sell direct, they sell through local suppliers, and local suppliers had higher prices than where I got this pipe, which was Menards. So I had to drive to Menards, the closest Menards to me, which is luckily within 25 minutes of my parents' house, so it really wasn't that big of a deal to go get the pipe myself. You know, it fit in the back of my truck pretty easy, it was sticking out one side. I think some of you might have seen the picture that I posted a while ago. Anyways, I'll show it here again. So it didn't stick out that much on the one side. And speaking of money, if you're interested in contributing to this project, you can support me through multiple different means. First, obviously watching my videos helps because YouTube gives me a little bit of a cut of their advertising revenue. I guess, special plug here, just so you don't miss my videos, hit that subscribe button. And then there's a little bell there, click that too, and then you'll get notifications when I do post new videos. So other financial ways you can support me is Patreon, PayPal, Amazon storefront, and buying me a gift on Amazon. I have links to all those in the description too, and I think Patreon at the end of the video too. I think I have a link there. At least I will put one there. And for the calculations, I used a spreadsheet that's available on this guy's website. He sells a bunch of different Turgo spoons and Turgo runners and turbines, which I think I'm going to use for my final turbine, but I'm not exactly sure yet. That's still in, I'm still thinking about that. To get the spreadsheet, I went to how-to guide here and technical information. And I went down to this pipe dp.xls, and that seems sufficient for my uses. There are other spreadsheets here, like this one has a advanced pipe friction, and there's other cool, useful information sheets here for turbines in general. And now let's go over to the spreadsheet and see what this looks like. And I have modified it a little bit. This is not what you'll see. You'll see just something more like this. And I might have even modified some stuff in here. I don't recall. This was many months ago that I did this. So I modified this spreadsheet to have multiple different pipes here at once. We can see the different sizes. Notice that these sizes here are in inches, decimal inches. And it may not be a nominal dimension that you're familiar with. Like this 0.82 is actually the inside diameter of a 3/4 inch polyethylene pipe. 1 inch, 1.25 inch, which is the largest commonly available locally without special order. And then special order, you get into 1.5 inch, which is what I'm using here, and then 2 inch. So this is 1.5 inch and 2 inch at higher flow rates here. Now, what I did is I just created multiple sheets here with the different size pipes. Start with the 3/4, 1 all the way up to 2 inch here. And this does also take into effect different geometry of the pipe system. So I have here a T if I'm going to split off into 2 different jets. I have at least 1 coupling, maybe 2. Unions, stuff like that. But I'm planning on having it pretty open and free flowing, so the fittings here won't be as huge of an issue. And then the pipe roughness factor, you can change whichever one you're using here. In my case, I'm using obviously this drawn tubing, which would be poly. Very smooth inside pipe, actually. Let's look at the different pipe sizes and how much power they make given... Excuse my daughter. Given different flow rates and a set height here. It appears that I still have this at the old one. Okay, that fixed everything now. This static head height, this is strictly elevation gain, and then this is my pipe length. I've measured, like on Google Earth or whatever, different pipe lengths, and I never get anything over 800. It's always like 760, 780 feet, so I figure 800 feet should be good enough. If I have to, I'll go get another section of pipe, but I hope it's enough. Okay, going back to this chart here, we can see the 3/4 inch pipe. Anything over, we'll say, what is this, 12, 13 gallons per minute. At higher flow rates, that will have a larger nozzle, and we can actually see here nozzles increase in diameter. Any larger of a nozzle, and you're going to be having the water in the bottom of the penstock actually creating a vacuum and cavitation pockets in the pipe, and maybe even collapsing the pipe. So that's not desirable. I don't even have like the rest of it graphed here because it's like not even a realistic condition. And then the next size up pipe, this 1 inch pipe, has the same issue, and we get actually quite a bit more watts out of it. And our peak watts here we can see is 300 watts out of 1 inch pipe and 157 watts out of 3/4 inch pipe. You can see as the jet size, the nozzle size here goes up, pipe friction takes over, and we actually have less pressure at the nozzle because the water's being slowed down too much. And then up here we have 1.25 inch pipe, which actually would potentially work, and then 1.5 inch pipe, which is what I'm going with, and then the 2 inch pipe. Now, the highest flow I've ever seen was at 30 gallons per minute right here, and we can see that the 1.5 inch pipe does 829 watts. The 2 inch pipe gets 953 watts. So 829, 953. So that's 124 watts difference for a very small portion of the time. realistically, we're looking at 15 to 20 gallons per minute. So if I don't have 15 charted here, but 528 versus, come on. Okay, I can't seem to click on that, but I can actually go to the spreadsheet here for 1.5 inch, and that was 16 gallons per minute. Oh, should be this one here. Come on. 506. So 528 watts. 528 watts versus 506. It's like an operational flow. So that's not a huge difference. There's probably other ways that I could spend that $300 difference in pipe to gain efficiency, or other power sources like buying solar panels, which would make up any difference there. I also have charted here on the right side efficiency, and we can look at the peak efficiency of these two turbines, or these two Penstock selections, at 14 gallons per minute, which is 95, and 32 is, well, we'll go 30, which is 82%. And then for this one, we're looking at 98% for the 2-inch, and then 94%. So realistically, 2-inch would probably be the best pipe here to use all of the potential power if you had no other sources of power and you wanted to just spend as much money as necessary to get what you need. But I'm not doing that, so I'm going with the 1.5 inch. A few other things to look at here. So how does pipe friction come into play here? Well, as the water flows, your pressure at the nozzle will decrease. And over here is the PSI of your nozzle pressure, also known as a dynamic pressure. Dynamic as in the water's flowing. Your static pressure will be a little bit higher than this. Actually, pretty close to 110 PSI is the static maximum pressure that we're going to see. That's why I chose 125 PSI pipe, just so we have a little bit of a safety zone there. Safety factor. Factor safety. I'm not sure which one it is. It always confused me which ones those were in college. So as it's flowing, this is 2-inch at 14 gallons per minute. We're going to be seeing here 108 dynamic PSI versus 110. So we're losing 2 PSI to friction. And then over here, we're going to be losing 110 to 105. So 5 PSI to friction. And then we'll look at the 30. So that's losing 20 PSI to friction. And then over in the 2 here, this is going to be losing only about 6 PSI to friction. All right, real quick, I've added in another function here that would affect performance of the pipe, but only in freezing weather. Now, I'm not burying the pipe because I don't own the property that the pipe's going to be laying on. Even though I do have permission for the pipe to be there, I also don't want to have to bury it, because that would be a near impossible task without a $100,000 excavator that can climb mountains and removing lots of trees and stumps. So that's a non-option. So to keep the water from freezing, we're going to look at time it takes for the water to get down the hill. Now we're only going to be looking at the higher flow rates here for these pipes. And this is going to take 6, so this is minutes, 6 minutes for the water to go from the top to the bottom. And in that time, it's not going to be able to drop from, we'll say 52 degrees that it's coming out of the ground down to 32 degrees. And then also the phase change difference. So I have no fear of this freezing. I will have to insulate the turbine house at the bottom to keep anything in there from freezing if there's any drips or splashes or anything like that. So that's something I'll have to be aware of. Also the 2-inch pipe, we can see here it takes a little bit longer to get to the bottom, 10 minutes versus 6 minutes. So 10 minutes, I still don't think it would have an issue with freezing, but it would be more of a possibility the longer the water is in the pipe. And also flowing at a lower velocity. So a faster velocity, here's our velocity in feet per second of water through the pipe.
faster velocity will mean less likely to freeze, also just due to the motion of the water. Something that doesn't change very much between the two, between the 1.5 and 2 inch, here is the velocity of the water coming out of the jet. And in this case, it's 124, 125 feet per second. And in this one here, it's 127. So it's not a huge difference there in the velocity. The larger difference, let's stick on one here, is the nozzle diameter, 0.212 versus 0.214. Okay, that's not much of a big difference either. And let me get you this velocity here in terms of something that you're familiar with. Okay, real quick, I added it in. Here is your velocity. I suppose I can do it in meters per second too. Okay, and we're back. I added some labels here and miles per hour. So we're going to see that the jet's going to be flowing at 85 miles per hour, and that's 137 kilometers per hour. Sorry I did everything in standard or Yankee measurements or freedom units. That's just what I'm familiar with working in. I do have an engineering degree. I could have done all of this in metric, but I don't use metric every day. Sorry. And finally, let's look at our watts here. So this is 448 watts at 14 gallons per minute. Now, mind you, this already has turbine efficiency and generator efficiency plugged in here, and I believe I did this. Yep. So that's approximately 70% overall efficiency up to the wire. Obviously, there are going to be other efficiency losses from the charging system and inverters, but I'm not factoring that in here. So 448 watts at 14 gallons per minute, and this at 30 gallons per minute will flow up to 829 watts through the wire. Now, if you disregard the efficiency here, that's over 1,000 mechanical watts coming out of the jet. So that's kind of why I'm calling it a kilowatt turbine project. It's more impressive to say that. Not that it's a 448 watt turbine system. It's just not the same. It's not as good for clickbait. I hate that word. But it's a factor. Sorry. We got to live with it. So I think that's all I have to say for the spreadsheet here, my calculations to determine which pipe and which size I went with. And it was pretty clear that the cost difference between 1.5 and 2 inch just wasn't worth it. It wasn't economically justifiable to pay the extra $400 or so, $350 to upgrade from 1.5 to 2 inch. And it's not just the $350 in pipe. Every fitting is quite a bit more expensive the larger you go too. So barb fittings, valves, any of that sort of stuff, unions or quick couplers, they're all a lot more expensive at 2 inch than 1.5. So that's another reason why I didn't go with 2 inch. And here we see that I'm replacing the rocks that I have at the bottom. I'm building a better rock wall. I just have a little bit of too much water flowing over the edge there, and it's eroding the bottom. So I want to prevent that erosion. So special thanks to these Patreon contributors, or patrons as they're called, I guess. Active at the current time of filming: Alex Benz, Michael C. Darcy, Alex, Richard Shaw, Johnny Collin, Hans Peter Feld, if that's spelled right, or pronounced right, John Omdor, Jonathan Wright, Sean O'Connor, IT Gardner, Brian Jackson, Austin O, Jack Splater, Adrian Cohen, Tyler Bisbee, John Marcus, Norbert Hobbs, Patrick Wagner, Scott, and Brent Rickard. And also to these former patrons who have donated money but have since left. You'll be missed, but your contributions are appreciated. Gerardo Robadillo, Blair Hames, and Eric. And a special thanks to these one-time PayPal contributors: Hans Igli, Jeffrey Roser, Jacob V. Gardner, Martin Thielander, and James Hensley.
All right, that looks a bit better.